So remember last time we talked about how in multiprocessors, if there's shared memory, that means that if one processor or one core writes a location of memory, that memory location becomes visible to everybody else. So there is it actually started out as a preprocessor, but now it's more part of the language. There's a library called OpenMP. And most of the time when we want to parallelize something in high performance computing, the things that are easy to parallelize are loops. So for example, if I have, oh, what can I draw? Gotta put the pen on. If I have a for loop, I don't know. I don't know, 100,000. Okay, so I have this for loop, and maybe in the loop I'm doing something like a sub I equals, b sub I times c sub I. Now nominally that is order 100,000, right? And the way I can break that loop up is by maybe I have two processors, and the first processor is going to go from 0 to 49999. And the second processor is going to do indexes from 500,000 to 99999. Right? So I can divide the problem up in two. You can do this manually, and you can do it using a library called pthreads, which basically you're going to create a bunch of threads. Each thread, let's say, is assigned to a different core, and then you divide the loop up. What OpenMP allows you to do is put a pragma here. I think it's pragma OpenMP. I can't remember.
OpenMP parallel 4, I think.
Yeah, parallel 4. So basically, it's going to take that loop, and you're going to tell OpenMP, there's an environment variable you set, you say like OMP underscore num threads is 2, and it will divide this loop up. It'll do some analysis and figure out, oh, I can actually launch 2 threads and change the loop indices, right, for this loop. And so it does that for you. It's a very crude way of doing things because it doesn't know, for example, if you have what's called a loop carry dependency, where maybe this is a recurrence relation. So this is like a I minus 1, something like that. So this a sub I depends on the previous a sub I, and it will have trouble parallelizing that loop because it assumes that once it breaks up these loops into 2 loops or 4 loops or however many threads you have, that those loops are independent. Okay. Now, what enables this to work is the fact that there's a shared memory machine. So everybody has access to the array A and the arrays B and C, and they're all in the same address space. Okay. So OpenMP allows you to parallelize things. In our machine, it will be within a server node, because within a server node, all those cores are in the same coherence domain. That is, they share the same memory. And so even though they have caches and there's all sorts of stuff going on behind the scenes to keep the memory consistent, that's all kind of invisible to us, except from a performance standpoint. Okay, so in a nutshell, when you go through the exercises, you can write a loop like this. You can set OMP number of threads, run the program, and you'll see it speeds up. In this case, it'll be fairly linear with the number of cores because there's, if I get rid of this recurrence term, the loops are independent. Okay. There's not much more really to say about it. When you go through the exercise, you'll see there's like different pragmas you can try. There are some other things that, you know, if you take 260, or if you've taken 260, like Kyle, there are some synchronization primitives that happen between the loops. For example, I have this loop up here doing some computation, and another loop down here doing some computation. and the second loop relies on the A that's computed by the first loop. There's an implicit synchronization barrier here, which means that all the cores are going to run, and then they're going to wait for each other here before they start the next loop. And sometimes you want that, sometimes you don't. The default behavior is to wait. Okay. Now that generally is fine unless one of the cores has a lot more work to do than the others, in which case everybody's going to wait for the slowest core, and you're not going to get the speed up that you expect.
Professor Shane, I have a question.
Yeah.
So when I was looking in for the Cuda stuff, they talked about each block, each grid has many blocks, and each block has many threads. I'm not sure if I messed up the order. So how does that come into play when doing the parallel computing? What is the logic? Computing
Okay.
logic?
That's a great question. Can you hold off on that? Because the way Cuda does threading is different from how we do it in OpenMP. There's a thread hierarchy in Cuda. And it's highly tied to the hardware. And so if you just hold, that's a great question, but probably maybe I should do GPU last because that's probably the most complex one. Okay, so this is OpenMP. Any questions about OpenMP?
With the shared memory paradigm with OpenMP, how does that, I guess, get affected when you start pinning NUMA domains on certain CPUs? Or
Oh, okay. So when you start pinning NUMA domains, there are scheduling hints. So OMP num threads is kind of the most generic thing you can do. You can basically tell how many threads do you want. And if you don't tell it, it's going to pick some number. I don't know how it does that. There are other scheduling hints you can tell it, like, hey, I want these threads to be assigned to these certain cores. And there's a number of ways to do that. First of all, when I divide this loop into workers, there's kind of 3 different ways I can do it. Say I have 4 workers, right? So I can divide them by saying, I'm going to take a piece of work and divide it by 4 so that the first quarter goes to the first thread, the second quarter goes to the second thread, right? So I might divide this loop into fourths. Like here, I divide it in half, right? That's called block assignment. And each of those blocks can be assigned to a thread, which is on a core, which is in a NUMA domain, and so forth. The other way to do it is say, take the work and mod 4. So if you imagine this loop iterations 0, 4, 8, 12, 16 will all go to thread 0. Loop iterations 1, 5, where am I at? 9, right? All the ones with residual 1 will go to the second thread and so forth. That's called cyclic assignment. And the third way is block cyclic, where I both divide and take a modulus. So maybe the range of like 0 through 2, 0 through 1 go to the first thread, and 2 through 3 go to the second thread, and 3 through 4 go to the third thread. And all these are kind of scheduling hints you can give to OMP. These are all hints. The machine could just treat them as no ops if it doesn't implement them. In fact, OMP pragmas themselves can be ignored. So like if you run on a machine that doesn't have OpenMP, this program will still run because all I've done is added these pragmas. I actually haven't changed the code. And so it'll run in a serial way. So to answer your question, I guess there are a bunch of hints. And one of the things you might want to play with, obviously the programs we're going to have are much more complex, is how do you reduce the cost of communication? So the coherence domains within the AMD chip, the AMD chip that we have, or the one we'll likely have, is made up of a bunch of chiplets. Each chiplet is a bunch of CPUs and some cache. And those are assembled into a bigger package, basically called die on die. So they take these little die and they put them on another die, and then that die provides interconnect and so forth. So if you want to keep all the computation, say there's 16 processors on one of these chiplets, if you try to keep all your threads on that one chiplet, say you only have 16 threads, you'll probably get better performance than spreading those threads out amongst 16 different chiplets, right? Because the communication overhead is going to be lower. That's not always true. If it's latency, that's the issue, that's probably true. If it's bandwidth, that's the issue, you might want to spread them out because each of those chiplets has a fixed amount of bandwidth. And if all those threads need to access main memory, for example, you might be better off spreading them out, right? So you get more bandwidth, you get higher latency, but more bandwidth. So those are the kinds of things that you'll want to play with if you have an OpenMP application by giving different kinds of hints to the scheduler. By the way, this all runs kind of in a, well, it doesn't have to, but in our environment, it's probably going to run in some kind of job scheduler. And you set some attributes that go along with the job and say, when you launch this job, set OMP num threads to this, set the scheduling policy to this, you know, do the following things. And they're all hints to the system, which again, it doesn't have to obey. And then you kind of measure the performance and see, you know, if you can characterize which of those scheduling policies, thread assignments, number of threads gives you the best performance. Does that make sense? Okay, so this is real high level, but just, you know, as you start to play with it, you'll see some ideas about how to play with the scheduling policy. So let's clear the board and talk about MPI. Okay, so MPI is pretty low level. It's a messaging library. It's not the lowest level. If you wanted to create a parallel program without an MPI on a cluster of processors, you could do it by sending messages over whatever protocol you want. You could send, if you've heard some of these terms, I'm sure, there's TCP/IP, there's UDP. These are all kind of ways of sending messages over a high-speed network. And in our case, we're using InfiniBand, which has its own set of primitives for sending messages on a network. Things you have to be able to specify in a message are things like an address. So that's who do you want to send the message to? And then there's the message itself. And then there's usually some kind of check, right? What you care about is this part. And then there's some other things that are encapsulated in the message, metadata, if you will. That's like some checksum or some kind of CRC or some kind of error checking. There's also some meta information like how long the message is, right? You have to say how long the message is because you don't have to embed in your message, you know, process until you see this token. You just want to say, hey, I have a message I want to send, and have the library take care of like, oh, it's this many bytes. It needs to go here. How does it get there, right? I don't want to have to specify if I want to send from this machine to this machine, I just want to give the address of this machine. I want the network to figure out, well, what's the best way to send it? Is it, you know, through a series of other machines? Is it through a bunch of switches? Is it through a router? Just like when you send an email today, you send an email to somebody, you don't have to specify how the email gets to them. There's some routing mechanism that takes care of that. But you can certainly build at a very low level communication protocols where you do have to specify all those things. Just anecdotally, when email was first beginning, when the Unix machines were populated around the country, but there wasn't really an internet, the way you used to send an email would be something like this. Say I wanted to send to me at UCSD and say I was at, I don't know, another university, it doesn't really matter where. I would say, bang, I think a big node was IHP, Indian Hill, I can't remember, ATT4 or something like that. And then eventually there would be a UCSD here, and there'd be like some other machine on UCSD campus that had my account. So we would specify in an email the actual path that it would take to send an email from one machine to another, because what was happening in Unix was a bunch of dial-up connections. This machine would call a machine at UCSD and send a bunch of messages over the phone line. And that machine would forward it to a local machine, say in the CSE department. So maybe there's like a CSE machine here. So when we used to send an email, we actually had to specify the path that the email would take. And it was all done through a program called UUCP with Unix to Unix copy, which basically just copies these messages from one machine to another. So you don't want to have to do all that. And we don't. So that's what MPI does. It provides a means of sending messages from one machine to another. Now, it's still very low level because unlike OpenMP, you explicitly have to decide what to send from one machine to another. So you would do something like MPI underscore send, and then a bunch of information. Usually it's a structure that has things like the node you want to send to. Now, the abstraction here is that you don't want to have to know the actual address of every machine, for example, the expanse. You don't want to have to know the address, like TCP IP address of every machine in the expanse server room. What you're going to do instead is when you start an MPI problem, you're going to say MPI init. And you're going to tell it, hey, I want 16 servers, or however many you want. And I think there's an environment variable for this too. I might be rusty on this. Maybe somebody remembers. That tells you like how many servers you want. And then the scheduler, the MPI scheduler will say, okay, I'm going to make sure that you get 16 machines. And here are their addresses. As an MPI user, I don't care what those addresses are. I'm just going to refer to them as 0, 1 to 15. So I can send a message to any of those 16 servers by just specifying a number. And there's a number of ways to specify those names. The simplest one is just a linear numbering of machines 0 to 15, but you can also assign a matrix to them or a tuple of n dimensions if you want. So if you wanted to create the illusion of having like a 3D mesh of processors, you can do that by telling MPI, hey, I want like 32 processors or 64 processors, and I want 6 on a side. 6 on a side? It's a cube root. 4 on a side, right? And I'll specify them in a unit of a 3 tuple. But however you want to do it, it doesn't really matter. It's all, from MPI's perspective, it's all kind of a flat address space. So the difference between OpenMP and MPI is that the programs are actually going to say, hey, I have this loop, right, in my for loop from before. I did a million. Plus, plus. And now in this loop, well, there's lots of ways to do it. One thing I could do is actually break this loop into 2, and I could send that data, copy that data A and B from the wherever the problem originated to the nodes that are going to do the computation. And then those nodes all do their computation, and then they send the message back. The synchronization in MPI is done all through messages. So if I have what they call a team of threads that are running on a problem, I can say MPI sync, I can say MPI receive. There's a lot to this, which we don't really have time to like describe, and I can't remember off the top of my head. But when you start to look at MPI programs, like I think we have some simple ones like create an MPI program that forks 4 threads and prints hello world or something like that. There's a bunch of things that MPI provides that allow you to divide a problem to synchronization, send messages, receive messages, divide work amongst multiple threads. Okay, that's probably all I need to say about it at this point. Any questions on that?
what exactly is MPI doing? Is it assigning job to different threads?
It's facilitating direct message passing between processors or processes. Because a lot of the time, if you're running an MPI application on your local system, it'll spin up a process for every available core you have, and then you'll do the communication between each core base essentially.
Right. So the programmer is explicitly dividing the work.
Yeah.
Unlike OpenMP, where the compiler will do it, here it's like, okay, you've decided to divide the problem this way. Like, it's like, let's say you have a big matrix and you're working on, I don't know, transposing it or something. You're going to work on this part of the matrix. You're going to work on this part of the matrix. I'm going to send you your section of the matrix to work on, and then you compute this. So typically these kinds of problems, like in HPC, the place where people do this is where the parallelism is fairly easy to recognize. So the programs that probably be running in this exercise are ones that scale because they lend themselves to parallelization. If there's too much interdependency between the threads, then these kinds of mechanisms don't work very well because you end up sending so many messages back and forth that sometimes that communication overhead dwarfs the speed up you're getting. And you kind of, and like in my class, we'll do things like, hey, as you scale up a problem and each core now does less and less work, the amount of communication that core has to do becomes a larger fraction of its computation time. And you start to see like, oh, it doesn't speed up anymore. It's like starting to slow down as I add in more resources. If you think about the extreme, if I have a grid of, 1 billion points and say I had 1 billion processors, each processor is only doing 1 point, which takes it very little time to compute. But to distribute all that work amongst 1 billion processors and collect it takes way more time, right? So you can see if I had a matrix of 1 billion points, I'm going to see some speed up as I go from 1 core to 2 cores to 4 cores to 8 cores. At some point, it's going to start to slow down because it's just you're spending too much time overhead. Does that make sense?
So OpenMP is where the processor itself dividing the job during the parallel, but MPI is we assign specific tasks to each processor.
That's right. So in OpenMP, the compiler is doing it kind of, compiler plus the runtime system, because the runtime system is going to look at either you might give it like a -NP flag, or you set an environment variable, and the runtime system will see that and says, oh, you want me to create this number of threads. Under the hood, it really is not different from like P threads. It's just hiding all those details from you. It's kind of, you can think about it as like, probably, I don't know if this is true, but I would imagine it is like the early OpenMP implementations could have just been like a C to C translator, where you take a C input, you look at all the pragmas, and then you take that program and you add all the P thread stuff to it so that it now becomes another C program that's got all this P threading stuff built in.
I have another question. So for OpenMP, it seems like we're heavily relying on the bandwidth passing the data to the processor for this many data that it needs to process. For MPI, do we need to also care about the bandwidth, or do we don't need to care at all?
Well, you do care about the bandwidth because, okay, this is something that you'll have more control over. When we run on Expanse, I've never discovered how to do this, but maybe, I don't know, maybe Kyle, you've seen it. I don't, if we had an SDSC person here that could probably tell us. The way the machine is organized is servers, and the servers are in a rack, and those racks are in rows, and those rows are in the data center. So there are servers that are going to be closer to you, both in bandwidth and latency, if they're in the same rack. And then there are servers that are going to be closer than other servers because they're in the same, they're in different racks, but they're in the same row. And then there are going to be servers that are much further away because they're in different racks that are in different rows. So geographically, in the machine room, there are servers that are closer to you and further away. And usually that means the number of switches they have to go through to get to one place. Generally, these machines try to balance the bandwidth so that as you go up the hierarchy of switches, the bandwidth of the switches gets higher. So it's usually not a bandwidth thing, but it certainly is a latency thing. And so when you launch a job in Expanse, the scheduler's supposed to try like, oh, you want 16 cores. The first thing I'll try is, can I get 16 cores all in the same node? And then the second thing I'll try is, can I get 16 cores spread out all within the same rack? And then can I get them all within the same row? And then can I get them all within, obviously within the data center? So ideally, it's trying to minimize those things. I don't know how well it really does that. So one thing I should mention, though, is you can run an MPI program on a single server. So the library knows through the layers of networking stack, right? So if the message actually needs to go between servers, then it has to do, the kernel is going to do some copying. It's going to open a port, a socket to the network interface card, and then the network interface card is going to negotiate the communication between the sender and the receiver, and the message eventually gets copied from memory to memory using techniques like RDMA and things like that, which we can talk about a different time. And then, but if you make the send call on an MPI and the destination's on the same server, then a shortcut can happen, right? Because it doesn't need to actually use the network interface card. All it needs to do is copy from one memory location to another. And that's really fast because it's all shared memory. So all I need to do now is just, okay, copy this buffer to this buffer, and then I'm done, right? So you can run MPI programs without changing them on a single server, okay? Or a combination of threads being on the local server, threads being on a remote server. So in our 3-node system, you might find that, hey, I can just run this MPI program on one node, and that's enough parallelism to get good performance. Or I can split it across 3 nodes, and some of those communications will be faster and some will be a little slower because it's going over a network.
But you mentioned about rows. That doesn't mean physical distance from the server to the data center?
About rows?
Rows.
Roads? I thought you said rows in the data.
No, rows. So like, here's my data center, like Expanse. Here's a server rack.
Oh.
And there's a bunch of servers here, and there's a top of rack switch here. And then these servers can talk to one another within the rack by just going through one switch. And then there's a row of these racks.
Oh, a row. Okay.
Yeah. And then there's an end of row switch usually. And all these racks are connected. Their top of rack switches are connected to this switch. And so now I go through this switch to get between the racks. And then these rows are connected in the data center, right? So if you look from the top, from the ceiling, right? Here's a row of servers. And here's another row of servers. And these rows are connected together through another switch, usually. And so, so there's different hierarchies. And so if the scheduler can try to assign all your jobs within the same rack, you're going to get better performance than when it starts to spread them out. But it's not an easy problem to solve. I mean, because there's lots of cores, there's thousands of jobs running all the time on Expanse. And so it's kind of like a pigeonhole thing. It's like, oh, you want 16? Well, let me see where I can fit them. Let me try to do the best I can do to keep them close to one another, but it's a trade-off between how long do you want to wait and, for the resource, and how much penalty you want to pay for communication overhead. Makes sense? You won't have these problems because you've got a dedicated 3-rack system. So you guys can decide, hey, I'm only going to run one job at a time, or I'm going to try to mix them up. And that's actually another thing that can be experimented with, like what works best for overall team score. Okay, so you go on to GPU.
I have some.
Oh.
I just have a quick question. I don't know if I'm muted on Zoom. Can you hear me?
I hear you barely, Kyle.
Okay, let me shoot closer. Can you hear me better now?
Yeah, much better.
Just like I understand from a implementation perspective, I guess, which is more familiar, but like, what sort of like, for the perspective of the competition, what sort of like knobs are we gonna be able to tune for the, like what are we gonna have access to in terms of, like parallelizing the benchmarks and stuff like that?
So you can't really modify the source code.
For the purpose of the competition, I guess, is what I'm saying.
Yeah, so this is my understanding, and others can jump in. Like Kai probably have a lot of knowledge about this, but you generally we don't modify the source code. The only case I think we did, I don't know, which last year or the year before, we had to modify it because there was a bug. But when we found the bug, we had the committee and they tell everyone, oh, make this change to this file if you have trouble compiling this code or something like that. So generally, the options available to you are things like what compiler you're using, what compiler flags you're using, what libraries you're using with the compiler, and then so that's kind of compile time things. And then there's runtime things like what scheduling policy do you want to use? How many threads do you want to launch this thing with? What other kinds of things?
And some other, all the system stuff that you can normally edit. And I think you can edit the source code. You just have to notify the committee and then they look over your changes. Because I know we're gonna have to do this. We're gonna have to do that for at least one of the applications. It's the old Fortran code one.
Yeah, I guess this like a lot of the sort of like scheduling and like runtime decisions you might make might be specific to the parallelism available through the implementation, I guess.
Yeah.
Yeah. And libraries are a big deal. So like, you know, a lot of these codes will use a math library, and there are lots of different ones out there. And you just have to try different ones, and they all have different flags. Like, do you enable SIMD or do you enable AVX 512 or, you know, stuff like that? That's could make a difference. And even whether you use GPU or not, some codes are, you know, have both support both native and GPU implementation, and you can play with both and see, well, what works better for the size of problem.
The benchmarks will make all of these like available to us, I guess is what I've asked.
Yeah, I mean, some of them are beyond the benchmark. So they'll like give you a benchmark. It's like, here's the source. Now, typically for like the benchmarks like HPL, the vendor already has an implementation that works really well because they've tuned it because they want to get the highest numbers. So that's like the first place to start. It's like, oh, does AMD have a HPL binary that we can run? Now, technically, I think we're supposed to be able to build it ourselves. And so we can't just take the binary and say, we're just writing the binary. We have to be able to reproduce it, but that's usually a first start. It's like, they'll tell us, like AMD told us last year, like, hey, use these flags to get the best performance and use this binary. That's how we compiled it, and use this compiler. So for those kinds of things, it's pretty straightforward. For the other programs, which aren't really benchmarks, that's where like, you know, have to get creative, right, and try a bunch of different things. It's really hard. There's so many knobs to change that it's tempting to say, hey, we can just write a program to like try all the knobs and like create a graph. That's ideal, but a lot of times we run into other issues like just getting them to run, or you know, not having a good way to collect all that data. And so that would be ideal, but you know, maybe there's some machine learning aspect here. You can use some language model to tell you, like, you know, what's the best way to run it, and it'll authoritatively tell you, oh, this is the best way. Even
Just rotate on all the inputs and read the output.
so, yeah, that may be cool to play with anyway. I don't know if it makes any sense. It'll make it sound like, yeah, this is the best way to do it, but it may be lying to you. Okay, should I talk about GPUs next, or any more questions about MPI? I skipped over a bunch of like what are the 4 calls you have to do to start an MPI and an MPI, but they're just library calls, which, you know, you'll see from the tutorial.
When I learned about OpenMP and OpenMPI, I was mostly told that OpenMP runs on like the same system, but in a distributed system, that's when OpenMPI really shined. So what's up with OpenMP across distributed systems? Is that like
OpenMP doesn't run distributed. It's shared memory only.
Yeah, so it's messages with OpenMPI can run over the NICs, but OpenMP can't.
Well,
Right.
it's because OpenMP doesn't do message passing.
Yeah.
Yeah.
Okay.
There are ways to fake it out. And there are some systems that people build that are very large MPs that have coherent shared memory, but we won't have one of those. And the ways to fake it out are software libraries that can create the illusion of having a shared memory machine, but really what they're doing is copying things back and forth. And that wouldn't work very well for us. So yeah, it's a good way to think about it is OpenMP runs on a single node only, single server. Now, there are programs that have used both OpenMP and MPI where the developer has written the code so that it'll use both. So when you try to use a certain number of cores, it'll use OpenMP for local communication and MPI for remote communication. I don't know if any of the programs that we have this year have that. That's a lot of work, but it's possible.
I know that it exists for HPL, but it is a pain to tune. It is because you're trying to balance how the shared memory on the local machine is run and also how it's run when you do message passing.
Yeah, so that's another dimension, right, of things to
Yeah.
try. Lots more variability, lots more permutations. Okay, let's talk about GPUs briefly. So, okay, so I'm going to draw my GPU. So here's my CPU.
Oh, so
And
for CPUs,
Yeah.
no?
sorry?
So Zishan asked if is OpenMP and OpenMPI CPU only, and I want to say yes, but OpenMPI is actually just mostly just for communication. So it can be GPU coherent. Like I think last year we tried to get GPU coherent MPI running, and I think it was because of our Instinct GPUs that it was kind of not working. I'm not too sure.
Yeah,
Because I know
I don't know that much about some of the newer libraries. There are some coherent implementations for GPUs. Generally, the code that we'll be running is Cuda, because that is kind of the de facto standard, and that's actually the big problem we have. The AMD GPUs that we found last year is like, it's really just not there. Like there's a Cuda equivalent for AMD where it looks almost exactly the same, but almost is not good enough. Like that means almost the code will work or almost it will compile. And getting that last 5% to work, first to compile and then to work efficiently, is not a simple matter. If the developer originally wrote it with the NVIDIA GPU in mind. One of the issues with Cuda, which is a sidebar here, is that it is designed by NVIDIA. So even though it's kind of, quote, GPU agnostic, it really isn't. And so when people write their Cuda code, they're really writing it with a particular GPU in mind. And then when it might run on the AMD, but it won't necessarily perform, unless somebody puts in a lot of work. So, okay, so let's talk about GPU model, just a general hardware model. Here's my main memory, right? And that could be HBM, it could be DDR4, DDR5, whatever we're at now, DIMM modules. But basically I have my server board, and it's got tightly coupled memory with it, and a CPU, which the CPU in this case has lots of cores in it, caches, all that other stuff. Hanging off of this is a PCI Express, which is a high-speed bus. Okay, it started out as a parallel bus called PCI, and then eventually became high-speed serial links with PCI Express, and now we're up to PCI Express 5 now? I don't know.
5 are rolling out the spec for 6.
Yeah, so basically just higher and higher interconnect links. It's very interesting, actually, very interested in like the engineering behind it. Is that it's designing very high-speed serial links is really an interesting electrical engineering problem. And so there's a lot of innovation happening kind of in how do I make this basically point-to-point interface fast. So logically, it looks like I can put multiple things off PCI Express bus. Electrically, it's really just point-to-point links. And the way I put multiple things off PCI Express bus is have multiple links, or I have a PCI Express switch, which has a bunch of PCI Express links sitting off of it. So logically, all these devices look like they're sitting on one PCI Express bus, but electrically they're not, because there's no way to make these high-speed links work with multi-drop, right? They have to be point-to-point. So in any case, there's a really high-speed link called PCI Express, and my GPU is usually sitting off here. And it has its own memory. So you might see like you buy a GPU card from some vendor, and the vendor has like an NVIDIA GPU and a bunch of graphics DRAM. And that is a separate memory from the main DRAM. Okay, so how does this process work? So typically I'll be running around my C program here, and I make a kernel call. It's got a bunch of parameters to it. Actually, there's a bunch of Cuda calls here. Cuda copy. Cuda copy. I don't remember what they're called, something like that. So what's happening when we started using these GPUs was that the GPUs are a completely different beast from the CPU. They are not optimized for latency. They are optimized for throughput. So that means they have thousands of tiny cores in them, each one of which is very wimpy. It can't really do that much. If you look at the clock rates of GPUs, they're significantly lower than CPUs, because the idea here is, well, let's have thousands of these cores running at, I don't know, let's say a gigahertz or 800 megahertz, instead of having 16 cores running at, 4 gigahertz, right? Because these cores in here are big and power hungry, and these cores in here are tiny, tiny, and not too fast, okay? And that's kind of a conscious decision, because the problems I'm wanting to solve on the GPU are parallelizable. That is, I can divide the problem up into thousands and thousands of threads, and I can't do that on a CPU because I don't have thousands and thousands of threads, okay? So the first thing to observe about this system is that the GPU is actually sitting pretty far away from the CPU in terms of latency. Like here, I'm talking to DRAM, maybe I'm, I don't know, 80 nanoseconds away. Here, I'm talking to PCI Express, you're talking about, upwards of 1,000 to 2,000 microseconds. I'm not nanoseconds, like a lot of time, right? Maybe more than that. I have to think about that a little more. And this is a separate memory. So in the original model, what I'm doing is I'm taking my problem here and I'm copying it to the memory over here. So Kyle knows all about this. When in 260, we do matrix multiplication, and for the GPU problem, we take the problem that's in the DRAM on the CPU and we copy it to the GPU, and then we launch our kernel on the GPU to do the matrix multiplication, and then we copy the result back to the DRAM. Okay, so there's an overhead of getting started and getting the results back that for small problems is the speed up that you get on the GPU isn't worth it. Okay, so this paradigm, even today, where the quote this coherent memory and it's shared, it's still pretty far away latency wise. So in the newer libraries and implementations, they kind of merge the address space between the GD-RAM and the DDR-RAM, so the CPU can see both of them and GPU can see both. But they're still physically very far apart, electrically and physically far apart. So it's sort of like the coherence domains we talked about earlier with AMD CPU. Even though they're all in the same address space, some communication within a tile is going to be much faster than communication between two tiles or communication between two sockets. Okay, so logically they're the same, but there's still performance impact. So GPUs are really good at high throughput tasks that are going to compute for a very long time, right? Very long from a CPU's perspective. If I need to multiply a matrix that's the 64 by 64, it's much faster to just do it on the CPU than to do all this overhead of launching a kernel on the GPU. Does that make sense? Okay. So what is the computational model for a GPU? So as I said, there's a bunch of these little cores. And they're called, in NVIDIA's parlance, they're called streaming multiprocessors. They're just tiny cores that are not particularly fancy. They're getting fancier than they used to be, but compared to the CPU, the pipelines are fairly short, the frequencies are fairly low. They don't support things like, they may have a very crude branch predictor if they have any at all. They don't have much of a cache. If they have a cache, it's pretty far away. What else about them? Whereas a CPU might have like a super high performance vector unit. They'll have support for vectors, but it won't be very high performance. Okay, and the theory is it doesn't matter because these processors can be slow, but because I have thousands of them, instead of trying to, like on the CPU, I try to get very high throughput by throwing all this stuff in my vector unit, having to operate at very high speed. Here, I'm going to take, again, that loop that I had before, I'm going to divide it into thousands of threads. So maybe each thread is going to do like 4 loop iterations, right? And just divide it up, assuming that all the thread iterations are independent. Okay, there's a lot of assumptions that the GPU makes about the programming model that are not supported by traditional computer programming languages. Okay, if you run a C program and you get an error that happens, you should be able to bring up the debugger and all the instructions that have prior to the error will have completed, appear to have completed, and all the instructions after the error appear to not have completed. There's a bunch of hardware support we do in CPUs to make that happen, with speculative execution and different kinds of mechanisms that we use, like reorder buffers, things like that, to keep that illusion true. And we jump through a lot of hoops in the CPU to try to parallelize things and do things in advance. And if an error happens earlier, we throw all those things away. The GPU, because it's so simple, doesn't assume any of that. So once you divide all these threads, kind of the ordering in your program goes away. And that's not supported by programming languages like C, because the C program is supposed to have certain semantics. This statement happens for that one, this happens for that one. There's a linear order to these operations in the program. And in Cuda, that all goes away. So one of the big differences between Cuda and traditional programming language is that it's really not ordered at all. Okay, we're taking all of the things that happen in time. And so if, again, I go back to my example before of the loop, a million loop. So I'm going to divide that loop into 1,000, right? And each one's going to do, what is it, 100,000? 100,000, no, 10,000, 100,000, million. Yeah, so each one will do 10,000 iterations. And some of those loops may finish before others. Some of those loops may get errors, but the subsequent loops will still happen. And all that kind of is legal in Cuda. Okay, so there's a very specific programming model that goes along with Cuda that is, and in general, GPUs, that traditional programming languages don't support. Okay, so that's the first thing to know. So the second thing to know, first thing to know is we do these copies, copy the problem over the GPU, and we do the kernel launch, which on our CPU, in the simplest case, just says the CPU is going to wait. I'm going to wait for the GPU to tell me it's done, and then I will copy this data back and then go on my merry way. So in some of these programs that are really written for GPUs, the CPU is doing nothing more than launching the kernel and waiting. Okay, in some other instances, they try to divide the work, so that takes more programmer input to have the CPU still do stuff in addition to the GPU. things that it's maybe better at doing, or maybe it's just extra computation power you're using sitting there anyway, might as well use it. Any questions? Kyle, did you have a question?
Can't you have a asynchronous GPU kernel launch?
Yeah, in fact, this really is asynchronous. When I do this CUDA copy, that's what synchronizes it. So it is asynchronous, but the simple model is that it isn't. That makes sense. There's also multiple kernels, so you can launch a kernel on this GPU, maybe another on a different GPU, and have them running simultaneously. And a lot of the codes that are optimized that you're going to be running will probably do stuff like that. This is nothing, I don't cover this in my class. It just gets too complicated. But let me talk about the threading model. Okay. So I mentioned that the GPU has a bunch of these little cores. And at least in NVIDIA, they're called streaming multiprocessors. And these streaming multiprocessors, there's a bunch of them. Okay, so when the kernel launches on the GPU, there's a scheduling that happens, and there's a hierarchy of threads. So the highest level is called a grid. And in CUDA, it can be up to 3 dimensions. The grid is divided into blocks. Imagine this is, I don't know, say it's 10 by 10 by 10. So that's 1,000 blocks. Each of the blocks has threads, and those blocks can have up to 1,024 threads, I think is the latest ones. So here's my block. And it can have a bunch of threads in there. Those threads, this block gets assigned to an SM. So different blocks from the grid get assigned to different SM, and the hardware makes that decision. So one of the important things to do is to divide the problem into enough blocks that you use all the SMs on the chip. So I don't know what the latest, there's actually another hierarchy in V100, I can't remember what it is off the top of my head. But there's a course level scheduling that assigns these blocks to these hardware blocks on the chip. And you want to make sure you have enough of these blocks so that you can use all of them if you're optimizing for performance, not necessarily for power. Okay. Now, once that scheduling is done, it's fixed. This block gets assigned to this SM, and this block gets assigned to this SM, and they stay there. They can't move. So even if this SM finishes and it could try to finish up some threads from this other block, it can't do it. Okay, so the other thing that has to be optimal or optimized in these kind of problems is to try to divide the work between blocks evenly so that all the blocks have approximately the same amount of time, take the same amount of time to compute, or else you have an imbalance and you end up, like we had earlier, a waiting for the slowest one, right? You don't get any speed up when you're doing that. Okay, within these blocks, so here's my streaming multiprocessors, and all these little cores in here. These threads get assigned by hardware. Oops. The computer's getting slow. So I look at this thread block. It's made up of a bunch of threads. And when I say made up of threads, it really means that the hardware has some data structures to keep track of all these different independently executing threads. And it takes a group of 32 at a time and schedules them onto 32 different cores. And that's called a warp. And that scheduling happens within the SM itself. And again, once those threads are assigned to different cores, they run there till completion. They don't move around. Okay. The other thing that's happening in a CUDA program is that if I have a statement, I don't know, like add, let's say x equals x plus y. So this is a vector, actually. This is a vector. That's a vector. So while this looks like a scalar statement, what it's really meaning is, let's say there's a million different values of x and y, and there's a thread that computes each of those. Okay, this program is, these threads are kind of operating in lockstep. Within a warp, they're all 32 warps for 32 different threads are all going to do the add at quote the same time. Okay, so there's, unlike in the CPU where we have threads that are running that are kind of independent, even though I launch them at the same time, they're all doing x equals x plus y. They all have their own program counter. They all may take different branch decisions. They may do different things. To simplify the hardware in a GPU, all those threads are doing the same instruction at the same time. And if one thread stalls because of some reason, they're all going to stall. Right? If one takes a branch, the other doesn't. There's more details here we don't have to get into. There's things called thread divergence. There's the things that the programmer has to do to kind of maximize performance by trying to keep all the threads doing the same work at the same time. Okay, that's probably a high enough view, and probably shouldn't go much deeper than that because you won't be writing CUDA programs. So you don't really need to concern yourself with how this parallelism is done. But you are worried about things like, how do I allocate the kernels to GPU? If there are multiple kernels, do I do them serially on the same GPU? Do I try to do them on 2 GPUs? There might be in some of the programs some compile flags that let you mix using the CPU and the GPU. For example, I think on the HPL, wasn't there an option, Kai, where you could have the CPU do some of the iterations for you? And we played with that last year.
Custom build of HPL is kind of old.
Yeah, so I don't know, it may not make any sense anymore because the GPUs are just so much faster at some of these computations. But there probably is a threshold, like if the problem size is small enough, it might be faster to do it on the CPU. I doubt they'll give us one of those, but it's possible.
Or you can go on. I was going to ask, how does CUDA code differ from like compute shader code?
From what code?
Like code for like a compute shader for like graphics.
Oh, okay. That's a great question. So GPUs are really just GPUs. So GPU initially was a graphics processing unit, which was designed to do like 3D graphics.
Mhm.
And 3D graphics have a couple of things that are very common. So if you look at like the original like SGI graphics engine, reality engine, I think it was called, came out of Stanford. And what it was basically is when I want to do graphics, 3D graphics, what I want to do is take a point, which is in 3D space. So it's got an X, Y, and a Z and an alpha, which is the shading. And I want to transform that point. There's a couple things I can do to the point. I can rotate it. I can translate it. Rotate, translate, what's the other one? Shrink or expand it. Okay. So if I have a bunch of objects in 3D space, basically what I end up doing is multiplying them through a bunch of matrices. Each matrix supplies a transformation. I can translate a point, I can rotate it, and I can expand it or contract it, rather. Take 2 points, expand them, and contract them. So that's why GPUs are so good at like matrix operations, because that is like mainly what they're doing. Now, there are some other operations that graphics have to do. For example, once I move an object, is it still visible? That's called clipping, right? Or if I have 2 objects, one in front of the other, one blocks the other one. So I have to be able to do this computation in Z space to figure out, well, what's the closest to the viewer's eye? What object will they see? What would be blocked from their view? And so there are a bunch of units in the graphics processor that do things like clipping, which generally for general purpose computing, we don't care about. So that, but it's a very small amount of silicon area. Similarly, there's some other computations that have to happen when I do 3D graphics. Like so typically 3D graphics is like a bunch of triangles. So I've got I can describe a triangle with a little vector that describes the points of each of the triangles. And then I want to, prior to like ray tracing, the shortcut was, hey, this triangle needs to look like this color. And this triangle over here needs to look like this color. And maybe that color has like dots in it, or it looks like a piece of wood, so it has a texture, or it looks like water. And so I have this thing called shaders, which apply, basically paint the pixels within that triangle to be that color or texture. And so there are a bunch of hardware and GPUs to do that too, which again, don't use that many transistors. And so the gaming or graphics GPUs have this extra hardware, and even the GPUs probably still have them because it's more expensive to make a distinct piece of silicon than to just say, hey, this is the server GPU. It doesn't support that. And probably still there. But yeah, those are things that GPUs have that we don't really use in HPC. Now, maybe if you're doing a bunch of rendering and stuff, you will use them. And some of the ray tracers might be kind of interesting. I haven't looked at if there's any, there's probably some papers on how people have used them to do other kinds of computations. I bet you could actually, especially for like particle motion and things. But anyway, so that there are a bunch of other hardware in the GPUs that in HPC we don't generally use. We're just using them basically as giant matrix multiplication engines.
I see, because I know on the MI 200 250s we had last year, they didn't have a driver for graphics. Because David was trying to, or at some point was like, if I just made a graphics like a computer so I can do graphics.
Yeah, yeah, it'd be cool. But yeah, they may disable them, or you know, a lot of times in the software they'll say, "Oh, this is an MI200. It's a server GPU, so it doesn't support these APIs." And a lot of times the hardware vendors. So when you have a really big chip, the bigger the chip, the lower the yield. That is, there's a certain defect density in silicon. And so the bigger the chip gets, you're going to get defects in the silicon. And so the bigger the chip, the more the defects. And so, okay.
Is that the reason why AMD moved to chiplets for their CPUs?
That's one of the reasons. There's two reasons I can talk about. But before I get there, so we talk about defects. So the bigger the chip, the higher the number of defects. And so if you need the silicon to be perfect to sell it, you're not going to sell very many, right? Your yield goes down because the number of good die that are perfect is inversely proportional to the size of the die. So typically, like in a GPU, they build in a lot of redundancy. So like maybe they advertise 1024 cores in each of those SMs, but maybe each SM actually has like, I don't know, 1300 cores, right? So only 1024 need to be good. So there might be some extra ones that are good, but they're not going to use them. And at the manufacturing time, they test them all. And then they typically have these fuses, which can be blown by a laser, where they'll fuse out the cores that are bad. Or they'll fuse in all the good ones, and you only advertise 1024. So the same thing happens if they have different levels of GPU. So maybe they charge a lot of money for the ones that have a lot of capability because the yield was really good on those, but that means there aren't as many of them. And maybe there's some where the yield wasn't so good and they can fuse out a bunch of the bad cores and then sell it as a cheaper GPU with fewer cores. So CPU people do the same thing. And one of the reasons to go to chiplets is to solve the yield problem, but it's actually not the primary reason, because when we look at chiplets, the yield is actually the yield of the entire chip. That is, I have to take these little die and put them on the big die and then test the big die, and it all has to work. And we lose some chips when we try to do that chip on chip, because there's a certain manufacturing cost to doing that. There's going to be defect density when you try to do that. You know, not all connections will be good. Sometimes the chip will get damaged when we try to do that placement. There's all sorts of things that can happen. So the more steps you have in the process of manufacturing chip, the yield, overall yield goes down. one of the primary reasons for doing the die-on-die stuff is process technology. So if I have to build, on 3 nanometer technology, the yield is going to be pretty bad for big chips because it's brand new technology. But if I can build small chips, my yield will go up, even though the defect density might be really bad, right? Because it's a new process and it's expensive. And if I can build, for example, the other reason is like if I'm putting a bunch of peripherals on my chip, like PCI Express and DDR controller and stuff, it's expensive to port that technology to 3 nanometer. I already have it working in 12 nanometer or 15 nanometer or whatever the process was. It's no advantage to port it to 3 nanometer. It just costs me money, right? It's already working in 12 nanometer. Why would I put in the extra engineering effort? So it saves them a bunch of development effort to say, hey, I don't have to port these other things like the memory controller, PCI Express and USB and all that stuff. It's like it already works perfectly in the other technology and the yield in that is going up. So why don't I just keep making those other chips where it doesn't matter how fast they are because it's not buying me anything, and just use it where it matters, like on the cores. So that's a reason, that's one of the main motivating reasons for going this multi-chip. If you can get the multi-chip process to work well, which I credit the cell phone industry, because that's, in my career, we always talked about doing these multi-die and we always got pushback from either management or silicon manufacturing side. It's like, oh, your yields will be terrible because this, doing these multi-chip modules is, you're going to lose a bunch of chips when you try to do that. Also, it's kind of a sourcing nightmare because if you're buying DRAM from Micron and you're buying, doing the subject to TSMC, and maybe you're trying to build on different processes at TSMC, and then you need the house to actually put the die together. So it takes a lot of manufacturing wherewithal and also industry connections and volume to bring all those parties together. And so the companies I worked at were probably not big enough to be able to, tell Samsung, oh, you're going to sell a spare DRAM die, right? They were like, well, why would we do that? But if somebody like Apple or Qualcomm comes along, they're motivated to make it work. And so I think the high volumes in like cell phones, where they started doing this first, really made it like, hey, this is really doable by these big guys, and now it's all over. Okay, so that's a lot of me talking. Any questions about GPUs? Did I cover what you wanted, Jijan, before? You had a question about?
I have a question regarding to the GPU. You in your previous graph, you draw a block and then leads to a warp. What is a warp?
A warp. A warp is simply a group of threads. So I've got this, let's do 2 dimensions. So I have a 2-dimensional block of threads. Say it's, I don't know, 64 by 64. Each of those threads has a coordinate, an X and Y coordinate in Cuda. And the way the hardware schedules the threads is it does 32 threads in the X dimension. That's called a warp. And the warp will be issued to a group of 32 cores. The reason that matters is because it comes back to the computing model. There's a bunch of things that happen in the GPU that we would never do in a CPU. Imagine that each of these threads is loading some array, A sub I. Okay. And the way I wrote my CUDA code is that thread 0 loads A sub I. Thread 1 is going to load A sub I plus 1. Thread 2 is going to load A sub I plus 2, and so forth. So they're going to load 32 consecutive entries of A. What the hardware will do in the GPU, it will say, hey, you're loading from location A. You, thread 1, is locating from location A plus 4. You, thread 2, is loading from location A plus 8. So the hardware will say, hey, the GDDR RAM is optimized for bandwidth. That means it does things like, if you ask for a byte, it's going to give you like 128 bytes back, right? Because if you know how DRAM architecture works, DRAMs are organized in tiles of arrays, which are rows and columns. So once I open up a row of DRAM, I get all these columns for free. So it's pretty cheap to access one row and get a whole bunch of data back because it's optimized for bandwidth. If you think about the way graphics works, like the early days of graphics, when you're painting a screen, I'm accessing successive locations in my frame buffer over and over and over. So it's really designed for like access this pixel, this pixel, this pixel, this pixel. They're all adjacent memory locations. And so the GDDR DRAMs are optimized for that because they're not going to do random access like CPU DRAMs. They're optimized for long blocks of consecutive data. So what the GPU does is it looks at all these loads and says, hey, you're asking for 32 consecutive words of memory. I can ask the DRAM one time for A, and it's going to give me all 128 bytes of data coming back because one transaction will do that. That's called coalescing. So the GPU will take a bunch of these independent loads from the warp and try to minimize the number of reads you're doing from DRAM. Okay. And again, you won't have to worry about this. The code, this is the kinds of stuff that people who wrote the code tried to optimize to like, oh, how do I make the loads coalesce so that I minimize the amount of DRAM traffic I have, which will improve my performance, right? Because the faster I can get the data into the CPU, we talked about computational intensity last time, the higher my computational intensity, because the less time I spend moving data around, the more time I spend doing computation. So that's called load coalescing. The same thing happens with stores. And all this is stuff that the GPU can do that CPUs generally don't do because it would break the programming model. So that's what a warp primarily what happens. And again, there's another reasons why the code is so optimized for a particular GPU, like people are spending a bunch of time. Oh, I didn't talk about memory hierarchy. Let me talk about that for a minute.
Professor Shin, another quick question.
Yeah.
So you drew it in 3D grid, and it has 3-dimensional blocks inside. Then is each block also 3-dimensional?
Oh, they're actually they're all independent. So I get a 3-dimensional grid with 2-dimensional blocks, you know, or 1-dimensional blocks. So the important thing is in Cuda, they can only be up to 3 dimensions, but they can be 1-dimensional. I can have a 1-dimensional grid with 1-dimensional blocks as well. Yep. I think the reason they're 3 dimensions is, well, there's reasons that they fix them up to 3 dimensions because the hardware has to keep track of all this stuff. And so if they made them arbitrary dimensions, then the hardware would have a hard time, like you'd have a harder time designing fixed function hardware for that. And the other reason is if you think about the kinds of problems you want to solve, most of them are up to 3 dimensions. So if I'm thinking about like particle simulation, I can divide a volume into voxels. Each voxel is a small 3D region that I want to simulate, and maybe each thread is responsible for simulating each particle within the volume. So I think that's the reason they chose 3, but like in our class in 260, we only use 2 typically.
So it is possible that we'll have a 3-dimensional grid, but inside that grid we'll have a 3-dimensional. Well, the dimension for each block is 2-dimensional.
Yeah.
Okay. Okay.
Yeah. Or you can have like a 2-dimensional grid with 3-dimensional blocks in it. Yeah. But you won't, these are stuff that you won't specify. This is all embedded in the program itself.
Okay. Okay.
What you will be able to do is things like there are vector units, like they have SIMD now in some of these GPUs. So you'll be able to play with a bunch of compiler options to see how it works out. You can Some programs will let you specify the number of threads. It depends on how the programmer wrote it. So you can play with that. What else can you play with? Oh, this is kind of modifying the source code, so maybe it's not fair. Let me talk about the memory hierarchies. So I've got my cores here, and they've got, so this SM, first of all, there's an instruction cache up here that belongs to this block, and all the cores, I believe, and they change this all the time, but generally they share the same instruction cache. And then there's a layer here called L1 or shared memory. Now, I've got most experience treating this as shared memory, but it can also be used as L1 cache. And this is shared by the entire streaming multiprocessor. So all the cores within this one block share the same L1 or shared memory. And then there's like a L2 cache, which is shared by all the SMs on the chip. And then we have DDR
What is this? Shared.
or HBM or whatever. So these all share here.
Streaming.
And a lot of these programs will treat this as shared memory. Eraser. Okay, so a lot of the programs will explicitly manage the shared memory. So remember before I talked about coalescing. Well, what happens is I load 128 bytes of data into the shared memory. And now every time I want to access that data, I've copied it to shared memory. It's a different memory address than what was in DDR. I explicitly do the copy in the GPU. And now I can access this memory with much higher bandwidth, much lower latency. So like in 260, we do this by taking a matrix multiply and dividing into tiles, and each of the small tiles of the matrix will be sitting in shared memory. And now I can do computations locally without going to main memory, which is very far away from GPU's perspective. The latency is very high. So GPUs, a lot of programs will explicitly manage the memory hierarchy in ways that CPUs don't do. The other difference is the register file in each of these cores. So a typical CPU, maybe I have 32 registers. In a GPU, I probably have 1,024 registers. I've got a lot of registers. So I can bring things in and keep like small matrices in the register file. And now I can do computations much faster because I've got single cycle access to the GPU registers instead of, I don't know, 10 or 12 cycles to shared memory. So that's another difference between GPUs and CPUs. All right. I don't think I have anything else to add.
Great. I mean, we're approaching a good wrapping up point. Because all that's left is for every member to like sort of run jobs on Expanse. Right.
Yeah, I think it's a useful exercise. Go run an MPI job, go run an OpenMP. There's some simple hello world ones you can try. And you can modify those if you want to, like, hey, let's parallelize a loop, like the loop I showed you. You could probably do that pretty easily.
Also, if you're interested, I posted the an MPI programming, I guess, tutorial or homework that I set up a while ago for my project cluster or project group for the last year.
Good.
And that sort of introduces like the basics of sending and receiving messages in MPI. And if you want to dive deeper, I just sent this. There's a spec manual for it. But it's a pretty good introduction for how to do MPI programming.
That's the way I learned implies homework.
Yeah, you just have to kind of play with it. And, again, you don't have to write the programs, but it's good to be able to play with the, basics of it so you get an idea. Well, how does it work? How do I launch jobs? How do I change the number of threads? How do we do thread assignment? Which a lot of that's going to be specific to our system too. depending on which CPU we end up with and what scheduler we use and stuff like that. Anything else?
No, I think we're good, and because like this week was primarily to like overview CPU and GPU stuff.
When can we get in NVIDIA GPUs?
I think we have access to them over Expanse, but if you mean for cluster stuff, I'm not.
Yeah, I don't think we still heard back from NVIDIA.
They are being, well, both NVIDIA and Supermicro kind of being unresponsive at the moment.
Exactly.
Well, what is it preventing them?
The GPU? I honestly don't know.
What is the what?
Like what's making them so unresponsive?
I have a sneaky suspicion that that it's really difficult to get resources. So last year I tried to get GPUs from NVIDIA, and that was right after kind of the Bitcoin market kind of imploded, and so a lot of they were having a tough time. And this year it's exactly the opposite. So it's not that they don't have money, they just can't spare the silicon. Like, okay, now the demand is super high because of large language models. And so I think it's going to be difficult to get like GPUs from pretty much anybody, because they can sell them or they can't make them fast enough, especially the big ones. So I'm running into the same problem with 260. I use Amazon, so I just use cloud. But I was talking to a guy from Google, and he was like, "Oh yeah, it's going to be really difficult to get you cycles because basically everything's oversubscribed." So
Are you teaching it the spring this year, or is it still the fall?
I'm teaching spring,
Okay.
so maybe things will change by then. But I'm going to try between now and then to see if I can enable Google. Maybe I have a connection now. I just met, so he works in the cloud. But he basically told me like, oh yeah, they can't, like, everything's oversubscribed. So that might be part of it. I mean, we're not, if they can give us a couple of GPUs, even if they can't give us all that we asked for, all the teams are going to have the same problem. So,
I mean, the teams that have the advantage is if they can just take it from their local university.
yeah, I mean, it would be nice if we could borrow some from SDSU. And maybe that can happen. I don't know. I mean, we might be able to ask them, hey, we don't even need to physically borrow them. We can use them for now. And then borrow them physically, closer competition. Unfortunately, I guess, actually, let me think about that. Yeah, that wouldn't, the CPUs in there aren't that different from what we were asking for. A couple of years older, but they're AMD, right?
Yeah, most of them are AMD.
Yeah. Oh, but the nodes that have the GPUs have Intel.
Oh, do they?
Yeah. I don't know why, but they do.
It might just be an old contract that's continuing.
Yeah, it might be, or maybe the drivers weren't ready at the time when, I don't know. Anyway, okay.
Oh, Professor Chin.
Yeah.
What's the difference between TPU and GPU? Because when I'm going for the collab, there's an option to choose TPU.
Oh, okay. TPU is the tensor processing unit. That is Google's AI accelerator. And it is basically a matrix multiply engine. There's a couple of versions of TPU. The first TPU was integer only, and it was good for inference. And now I think they're up to TPU v3, if not v4. So after v1, they came up with so the initial TPU was actually pretty low power. It's like 65 or 80 watts or something like that, but it only did integer. And then the ones for training were called TPU v2 through now TPU, I think v4 or v3, that support floating point. And they're much bigger, and they're like water cooled and stuff like that. So we probably, I don't think they sell them. You can rent them in the cloud. and they're generally optimized for like running TensorFlow. So, so like MLPerf probably would be good to use them, but general purpose, they're not going to be that useful. Okay. Oh, there should be one more thing about the GPU. So the latest GPUs, starting with like Volta, have a matrix multiply unit. So there's a small block, I don't know if it's small or not, but there's a bunch of blocks that will do small matrix multiplies, like 16 by 16. And so the way you do matrix multiply in those GPUs is you keep partitioning your problem small and small till you get to a kernel that is a 16 by 16. And then you send it to the matrix multiply unit, it does the multiply and then kind of accelerates things, because that's such a common operation, especially for machine learning, that they added these special matrix multiply units. All right, anything else?
I guess that's it for next week. Let me check the training schedule. It need to be next week.
I'm seeing next week is HPC topics. Oh, more GPU, OpenMP, and MPI.
I think the only difference in that week is Mary will be there. Maybe she'll want to cover other things. I'm actually not sure, but I want to start looking at the applications themselves. So if you have time, read over them, and we can go over it either next week, or do you want to do Thursday?
I wanted to do Thursday, but I'm gonna be busy with SCC and summer institute. Yeah.
Okay. No, we can push it to next week then.
What do you
'cause,
do?
How's the ML perf going?
Huh?
How's the ML perf?
How's MLPerf? I tried to look into the paper, but I haven't had any chance to look at it.
Alright, let's take the weekend then.
Yeah, we can take the weekend.
Should we-
Because I've been reading over my the repro paper, and I need to review a lot of this linear algebra stuff that I've been overlooking. Because that's the entire paper. It's accelerating Cholesky decomp.
Oh yeah, I need to read that too.
And then I'm actually kind of concerned about the Fortran code for magnetohydrodynamics, but apparently it should be fine if we can get is it Dan? No, Mary's husband. He does MHD stuff a lot, or he's familiar with it, so we could probably ask his help for.
I mean, we should have a pretty good Fortran compiler, I would think.
Yeah, but I meant in terms of like, because the competition isn't just running the application, it's also they'll interview you about your understand the code, it's what it's doing,
Yeah,
and if what's going on, it's kind of not great.
yeah. Okay,
Bye.
all right,
Right.
bye guys.
Bye, Brian.
You want me to end the meeting, or are you guys gonna keep meeting?
We'll probably keep meeting for some like logistic stuff, unless you want to stick around.